Hello everyone. For today we're going to work on a quiz about functions, so this is from 2.3, but specifically about one-to-one and two-on-two functions. So what do I mean with that? So let's quickly review what's going on here. So a function that we often just denote like this. So we have an A where the function takes its value, takes the input. So these are the inputs. And then we have a B where it takes the function takes its values. These are the outputs. But you have to understand this, right? The outputs are part of B, not necessarily all of B. And in fact, that is exactly what on2 means. On2 means all elements of B are outputs. Sometimes that happens, sometimes that doesn't, and that's exactly what we're going to check today. What does then one-to-one mean? Well, here it's more from the point of view of inputs. So if you now take two inputs, if two inputs have the same output, then they actually are the same. They are already the same. Okay? So, but we have logical, we have seen some logic, and so we knew that this is an if, right? If two inputs have the same, then they are already the same. Now we can take the contrapositive of that, and what does that mean? So we take the negation of they are already the same. So that means that if we have two elements and they are different, so two different inputs, then they should have different outputs. And that's, for instance, if you think of a one-to-one, a very simple example is social security number. To every person is associated a social security number, and of course two different people should have two different social security numbers, or it defeats otherwise the purpose of this number. So that's how general functions can be it's a very general concept. But let's work on functions that are defined, that we know from algebra, so they're given by a formula. And so one of the functions I want to look at is the function given by a simple equation, x squared plus 3. Okay. But I also, the function is not just given by a formula, I also have to say what are the inputs and what are the possible outputs. So I'm going to take three different possibilities. I'm going to take either the natural numbers as input and also as output. So in other words, I'll write it like this, right? So my function, I think of it from sending natural numbers to natural numbers, or I can think of it on the rationals, or I can think even very big and take the complex numbers, right? And now I can ask, well, is such a function one-to-one? Is such a function on2? Okay, and we'll look at all the possibilities. So we have a little table that we're going to fill in. But of course, it's not just yes and no. You know, whenever I ask a quiz, you always have to explain things. So let's think first about the first case here. Let's think about this one here, right? So I'm going to try to figure out what is going on here. What is going on in this part here? Sorry, for some reason might. Right. Okay, so what do we need to check? For one-to-one, so let's concentrate on that. We take two inputs and suppose that they have the same output. What can we say about them? So let's take two elements, A and B, in the natural numbers. These are my inputs, and we're going to look at what are the outputs. So I'm going to look at f of A, and I'll look also at f of B, and what happens if they are equal. So let's write down what that means. We have an A squared plus 3 here, and here a B squared plus 3 on this side, and they are equal. So we get some kind of equation that we have to solve and try to see whether this makes A and B equal or not. Well, you can see that you can cancel 3 on each side, so this becomes a squared is equal to b squared. And then we know from elementary algebra that actually there are two possibilities now. We can take the square roots, but remember, square roots are either positive or negative square roots, so this means that a is either b or negative b. So that's we always make this short notation like this. So it seems that if you take two inputs, if you took two inputs and you have the same output, that they still could be different, one positive, one negative. But then we think about the natural numbers and say, yeah, but wait, there are no negative natural numbers. So on the natural numbers, since there is no negative numbers, there's only one possible input, the positive one. And A and B must therefore be equal. So here we get, yes, that's 1 to 1. But let's go through the list of the other. So this is in the natural numbers, no negative solutions. But you see, the moment I go, for instance, to the rationals, that gets problematic because there are negative solutions, right? I could now have two different A's and B's that give the same thing. Like, let's take an example. In the rationals, take A equal to -1 and B equal to 1. What happens if then f of -1 is -1 squared plus 3, that is, let's write it up, -1 squared plus 3, so that is 1 plus 3, that is 4. But f of 1 is also, of course, 4. So there we see that it is not. So, and that is how you want to justify your answers. When it is 1 to 1, you give an argument why. When it's not, you give a counterexample. And this is, what is a counterexample? Means one simple case of two distinct inputs that give the same output. Okay. In some sense, disproving 1 to 1, saying that it is not, is easier because you only have to give one example. Whereas if you want to prove it is 1 to 1, you have to kind of give some reasoning, some argument. Now, it's clear that this problem that we had in Q is going to be perpetuated in C. We still always have two negative numbers. The same counterexample can be used again. So if A is -1 and B is 1, same, right? It's the same thing. Okay, there are rational numbers, but that's also complex numbers. So obviously here the answer is also not. So let's now focus on the onto part. So this was for the 1 to 1. So what about onto? So now we have the opposite question somehow. Now we don't look in the input, where the inputs come from, where the outputs come, where the outputs are. That are the natural numbers in this case. So now we have to ask, given a natural number n, can we find, let's call it B, sorry. Can we find A such that f of A is B? Right, I want to make this B, any B in the natural numbers, I want to make that as an output. In other words, I have to find an input for it. So, but again, this actually becomes an equation, right? Let's see what this is. F of A, what is that? Well, that's A squared plus 3. So now I have to solve the equation. A squared plus 3 is B. What am I solving for? I'm trying to find this A, right? Can we find? So we're solving for A. So solve for A. Okay, so that is A squared is B minus 3. So A is plus or minus the square root of B minus 3. Oh, you say there are two different roots. Well, I'm not trying to prove now that there is only one single input. I just want to find one. There could be many, right? So that the issue of the square roots having a plus or minus sign is not the issue. The issue is now, can I take a square root of every number? And that's clearly, again, a problematic thing, right? For one thing, B0 is going to be problematic. Problem, well, yeah, when B is 0. Let's say it that way, because when B is 0, then I squared is -3. A square can never be negative, right? And the square of a of a positive number can never be negative. Well, so it's clear then that the answer here is no. There are outputs, there are elements in N, for instance 0, that is not an output. What about Q? Well, it's the same problem, right? Because I'm gonna get this 0 is gonna give me again a negative, the equation was x squared plus, yeah, no, I did it right. I thought I made a mistake, no. If I do 0, I'm gonna get the same problem. What is the square root of 3, right? If I plug in b is 0, then I have to take the square root, well, I have to take the square root of negative 3, which is impossible. So the same counterexample shows that it is not onto here. But now about the complex numbers. Now we have to be careful. This is, we have to take a square root of a number. And the problem was if it was a negative number. Well, it's not the only problem, by the way. I can also not take the square root of 3 in the rationals. That's another problem. But for instance, I could have also included here, perhaps I should do this. Let me do this. I'm going to include one more case. Sorry, let me make my table a little bit longer. So I'm going to do the reals. And I'm also going to do the complex numbers. So with the onto, of course, that was one-to-one over the complex numbers. It doesn't get better, right? Once you have a counterexample, it stays a counterexample. Now, in the reals, we have seen, well, there's a problem. Because you could have negative numbers here. If you take the square root of this, if this number, b minus 3, becomes negative, for instance, if b is 0, then we don't have a square root. Okay? But if this number would have been a positive number, yes, square roots exist in the real numbers. They don't always exist in the rationals, but they do exist in the reals. But the problem is the negative numbers. But that problem is gone when we talk about the complex numbers. With the complex numbers, you can take the square root of a negative number, because the square root of negative 1 is I, and then, so you can always adjust that. So for instance, in the case b is 0, you would have the square root of negative 3, for instance, would be a valid input, which is what we normally would write as I square root of 3. That's a complex number. So there is an input. So, but of course, but just giving one example is not proving that the function is onto. You have to give an argument, and the argument is that over the complex numbers, this equation here can always be solved for a, because we can always calculate this square root. And we can, you see there are actually two possibilities here, so but that doesn't matter. Okay, so here we see that how these things can depend on the domain of not. Let me do another example and then we finish. G of x is x plus 1. Let's do that. So let's think about what happens over the natural number. Let me then we have our table back. I'm going to replace it here by g of x. So g of x is now x plus 1. And then we do the calculations here below for g. It makes it a bit easier, right? Okay, so for 1-to-1, again, the same thing. Suppose we have two inputs, a and b, and so they give the same output. Well, let's solve that. That means that a plus 1, that's g of a, equals b plus 1. Oh, but now you see immediately that this means that a is b. So yes, this is injective. Sorry, 1-to-1. Injective is another word, by the way, but in the book they say 1-to-1, so I'll stick to that word. So yes. Now you see that what I'm doing here actually really did not matter really what a and b were. They were natural numbers, but they could have been rational numbers, real numbers, or complex numbers. We're always going to get this. This equation is so simple, we're always going to get a is equal to b. So this is always going to be 1-to-1. So you see, this can also, you see, a lot of things can happen depending on which algebraic structure we work, but it sometimes just doesn't really matter much here. Now, what about onto? So now the onto problem. Remember, this is also solving equation. Now we take a natural number. Let's start with natural numbers first, and we want to solve the equation x plus yeah, so we, sorry, let me not write it that way, let me do it as we said before. So can we find an A in the natural numbers such that g of A is B, and that means that A plus 1 equals B. And you say, oh yeah, sure, of course, A is equal to B minus 1, so I can always do it. Are you sure you can always do it? No matter what B is, you're going to get an A. Be careful, because we are in the natural numbers, right? They're positive. So if you're subtracting something, you could become negative. And there's only one case here where it really is not going well. That is if B is 0. If B is 0, then A is minus 1, which is not allowed. Because so here the answer is no. But then, if you think a little bit about it, that's the only reason that can go wrong, right? Here. As long as you can subtract a 1 from whatever quantity you have, and you get the same quantity in the same range, of the same type, then it works. You can do that for the rationals, you can do that for the reals, you can do that for the complex numbers. So here it is actually simple that we have on 2, because we have the formula that tells us how to find A given B. And it is always, and that always gives us a good solution. So that's what the quiz will be on one-to-one and onto functions.